Hi everyone, welcome back. In this video we're going to be taking a look at binary search. This is a pretty important problem in Leetcode as it goes through the basics of how to solve binary search problems. And in this video I'm going to go through the basics of binary search, so if you don't know anything about it, that's fine. We'll go over the concept briefly, and lastly we'll try to implement this in Python. So let's first look at the problem. So we're given an array of nums. So for instance we have here -1, 0, 3, 5, 9, 12. And lastly, we're given a target. Okay, so this is the element that we have to search. So we have 9. So this means that we need to search where our target is in the array. Okay, so we have to pass through all these elements and find the 9. And as we've done that, we have to return the index of our 9. And so, well, someone who hasn't heard about binary search before might think, okay, well, let's just iterate through the entire array, then if we want the number, we simply return the index, right? But then it says that I must return this with O of log of n complexity. So, and if we iterate through the entire array, that's going to be O of n, right? And we don't want that because O of n, this is much, much slower than O of log of n, right? So we want the solution. So how do we implement this using log of n? Well, here we have binary search. It's a pretty important concept in computer science, and I think it can be confusing at first, but in reality it's very simple. So let's assume that we have a stack of papers. Okay, so we have here, for instance, we have a paper of someone with the surname that starts with A, then here another one that starts with B, another one that starts with E, then someone who starts with F, then another guy with, I don't know, let's say a U, here someone starts with W. Okay, and your goal is to say, okay, where's the paper whose surname starts with, let's say, U? Okay, and this is a U, by the way. Sorry, my writing's not very good. There we go. So, and then your task is to say, okay, where's the paper that has a surname that starts with F? Okay, and so in real life, what you would do is, okay, well, I'm gonna look at the middle, right? So I'm gonna get this stack right here, and I'm actually gonna put another element. I'm gonna put here a set, and let's say another set. And so I'm gonna look at the middle of this stack, and I'm gonna say, well, first, where's the middle? Let's assume here's the middle, okay? And then I'll say, well, is U smaller than F? In other words, if this is sorted and I want to get the F element, an element that starts with the letter F, do I want to look at this or do I want to look at this? Well, obviously I want to look at the right side, right? At the left side, because if I want to get the F element and this is sorted, I know that my F element, if we're here, it cannot be here because it's sorted, because all of these elements, right, they are bigger than F. So in this case, I want to search again, but I want to search on this subset. Okay, and so then you go, okay, all right, I'm gonna do the same thing again. So I'm gonna take here the middle. Let's assume the middle is on our B element, and then we say, okay, well, is B smaller than F? Right? Yes, it is. B is smaller than F. In this case, then, okay, well, since this is this is smaller than F, I wanna get something that's greater or equal to F. So I wanna use this bit right here. So I'm gonna search again, but this time I'm only gonna take a look at these two elements. Then lastly, we say, okay, well, let's assume my middle is on E, and we do the same thing. Is E smaller than F? Yes, it is. Okay, then I want to see my right subset, so I want to only get this element. And lastly here, we'll say, well, is F smaller than F? No, it's not. Is F greater than F? No, it's not. Is F equal to F? Yes, it is. And so in this case, I can already return where F is because I know this is the target. So that's kind of the main idea, right? Because instead of looking through every single element, notice that we've only looked at 3 elements here. We've only done 3 sub searches. And so this really reduces the runtime complexity by a quite significant factor. So that's kind of the main idea, right? I think it's a bit hard at first, but once you get the intuition of, well, I have a stack of papers and I'm going to look at the middle and then determine whether this is here or this is here. And then I'm going to say, okay, well, it's here. Then I'm going to look the middle again. We go right here. Then I take this middle right here. Then I take this middle right here. And lastly, we found the element. Okay, so let's just assume here that we have the left pointer. That's going to be here originally, the index number 0. Then we have the right pointer on the last element of the array. And then I'm going to compute the middle, right? How do I compute the middle? In the previous example, we kind of like did it visually, but I'm going to actually do the actual formula that we're going to use. So this is just going to be the middle is equal to my left pointer plus my right pointer. And then we divide it and then we floor it. This is why we have the double slash here to say that we're going to divide it by 2 and then we're going to floor it again in case we get a decimal point. So we get rid of it. And so basically this outputs in this case, right? Let's say this is 0, this is 1, 2, 3, 4, 5. This would be 0 plus 5 divided and floored to 2. So this would be 2.5, and then since we're flooring, this is going to be 2. So it's actually 2. And so we put the middle on the element number 2. So this is 0, 1, 2. So here we have the middle. And then we say, okay, well, is my element where the middle is, so is 3 smaller than our target? So is 3 smaller than 9? Yes, it is. If this is the case, which it is, then I go, well, I only want to look at these elements right here, right? Because I know that if 3 is smaller than 9, that means that 9 must leave to the right of 3 because it's sorted, right? And so I'm going to get rid of the middle here and I'm going to move the left pointer. And so if we had the middle on our 3, I want to move it mid plus 1. We do the plus 1 because we know that the target is not 3. So therefore it makes no sense to still look to include this element here because I know it's not the target anyway. So I'm going to put it here. I'm going to move my left pointer here. And I'm going to continue the process, right? So now we have here, this is index number 0, 1, 2, 3. And we do the same process. So where's my middle again? Okay, well, my middle is simply 3 plus 5. And then we floor it and divide it by 2. Okay, and so this is 8 divided by 2, this is 4, so we get 4. And so my middle is now here. And then I go through the 3 conditions again. I say, well, is 9 my middle? I'm going to actually put middle here just to make sure. So is my middle smaller than 9? No, it's not. Okay, is my middle greater than my target? So 9. No, it's not. Okay, well, if none of these conditions are true, then we know that 9 has to be 9, because there's no other option, right? I mean, we cannot have anything else. And so, since we know that 9 is equal to 9, we cannot return the middle. And that's it. We're done. We're able to look and find the target in, I think it was only 3 iterations, so it really reduces the time complexity by quite a lot. So this is the first example. Let's look at the next example now and see if we can solve it. So I'm gonna get rid of all of this right here. And let's copy the new example. So this is example number 2. We're gonna have here -1, 0, 3, 5, 9, 12. And our target is 2. Okay, well, same idea. So we put my left pointer here. We put my right pointer here, left and right. And I go, okay, well, it's my middle. Okay, well, first, my left is on this index number 0. this is 1, 2, 3, 4, 5. So my right pointer is on the right, on the 5th index, or index number 5. And so I compute my middle again. So this is going to be, well, 0 plus 5 divided and floor by 2. So this is 2. And so we do it again, okay, and we go, all right, my middle is going to be here on the 3. And I'm going to say, okay, well, is 3 is smaller than my target? Is 3 smaller than 2? No, it's not. Okay, next condition. Is 3 greater than 2? Yes, it is. So if this is the case, then I move my, basically, I want to move, since 3 is greater than our target, we can already discard this plate right here because I know the target won't live here. So we move the right pointer. So since we're moving the right pointer, I'm going to move it to the middle, -1. As I said, we discard the current middle because we know it's not a target, so it makes no sense to actually compute it, right? To compute it again. So I move my right pointer and I put it here. And I continue the iteration, right? So I repeat the process. So I go, okay, well, is, so 0 plus 1, so that's 1, divided by 2, and we floor it down. This is very important. And so this is simply, well, 1 divided by 2, this is 0.5, but since we're flooring it down, this is going to be 0. And I go again, okay, well, is -1 smaller than my 2, than my target? Yes, it is, right? In this case, this means that we can already discard this bit right here. And so what we would do is we move my left pointer. So remember the middle is here, by the way. This is the middle. I move my left pointer to middle plus 1. So my left and right pointer are going to be in the same place again. And so I repeat the process, right? Because it could be that 0, that could be our target, right? If our target was 0, then it could have been, right? So we have to check this again. So I go ahead and check again. So I say, and remember this is on index number 1, so we have put here -1, sorry, 1. And then I simply go, okay, well, 1 plus 1 divided by 2. This is simply 1. And so here I also have my middle. So I'm gonna put here middle. And I go again, I go, okay, well, is 0 smaller than 2, than my target? Yes, it is. Since this is the case, this means that we can discard this portion of the array, right? Because I know that my target has to live on the other side since 0 is smaller than 2. And so I move, in this case, I would move my left pointer to the right. So I say, well, left is equal to middle plus 1. So in this case here, I'm going to compute that real quick. So I'm going to have my left pointer on the 3, since this is middle plus 1. And now notice that the right is to the left of our left pointer. So the right is no longer on the right, but on the left. And the left pointer is now on the right and no longer on the left. This means that we finished binary search because we were not able to find a solution. So this is the exit condition. So I guess to sort of put it here simply, I'm gonna just write the main 3 conditions. So first, binary search is gonna execute as long as it makes sense, right? As long as our left pointer is smaller or equal than our right pointer. Because once this is the case, then we've broke the 2 pointers, kind of, I would say. And so we can already stop binary search because we won't find the element. It's gonna end up in the loop, right? So this is gonna be my exit condition, or I guess my while loop condition. Let me write this properly. My while condition. And then my if conditions. Well, I always look, okay, well, is my nums of my middle, so my current middle element, is my middle element smaller than the target? right? If this is the case, if my middle element is smaller than the target, basically that means that we can discard, right? We can discard what's on the left. And so we simply go, well, my left pointer is going to be equal to middle plus 1. Then the other case we can have is that nums of middle is greater than my target. And if this is the case, then I simply go, okay, well, right, middle minus 1, because we want to discard. Basically, we want to discard what's on the right, since we only want to see what's on the left in this case, since the middle is greater than my target. And if none of these conditions are true, then we return middle, because that means that indeed we found the element and that it's on the middle index. So that's kind of the main idea. I hope this makes sense. I would suggest you try to implement this on your own in Python, and we'll go over the solution in a second. Okay, welcome back. I hope you were able to solve the problem on your own, and now we will go through the solution. So, first off, we have to declare our left and right pointers here on Python. So I'm going to say left and right, and this is basically going to be equal to, well, the left must be to the left of our array, so that means it has to be 0, and our right pointer, well, that's going to be len of nums minus 1. Remember, we put the minus 1 because indexes start at 0. So that means that, for instance, let's quickly here come up with an example. So let's say we have this array. This is length of 6 because there's 6 elements, right? And so our len of nums, that is just going to be 6, right? But since this element is on index number 5, because this is 0, 1, 2, 3, 4, 5, then we have to subtract 1 from len of nums, so 6 minus 1, and that will give us the last element, okay? Then, once we have done this, then we have to think about the while condition. So basically we want to continue iterating as long as it all makes sense, right? As long as the left pointer is to the left of our right pointer. So while L, right, well, the current index of our left pointer is smaller or equal to your right pointer, then we want to continue iterating, right? So we'll first compute the middle. So as we said, the middle is your left pointer plus your right pointer. Then you floor it down by 2. So you divide it and then you floor it down. And then we check, okay, well, is our current element, right? So is S of middle smaller than our target? Then if it is, right, if S of middle is smaller than the target, right, then that means we must first look at the right side, okay? So we have to move the left pointer to the right. How do we do that? Well, we just simply say, well, our left pointer is equal to the middle plus 1. Then, if for instance the S of mid is greater than our target, then we can say, okay, well, since I'm looking for, let's say, 0, okay? And I'm on the 3, I want to only look at the elements on the left. So I have to move the right pointer to the left. So I say right is equal to middle minus 1. And lastly, if none of these conditions are true, then we return middle because that means we found the element. Now, if we've done all of this and we haven't found the target, right, that means that the target element is not inside the array, and so we return minus 1. And that's about it. I'm going to get rid of this comment right here. Okay, so this looks good to me, so let's submit the solution real quick. And let's see if it works. And lastly, we see that it works. So let's now talk about the design kind complexity for this problem. So in this case, we're not iterating through the entire array. We're making subdivisions, or we're splitting it into 2 each time. So therefore, the runtime complexity is going to be O log of n, assuming that n, so the nums array, is sorted. So yeah, that's about it. I hope you were able to learn something useful from this video, and I'll see you on the next one.